Welcome to the Stanford Scholar Initiative talk on two of the state-of-art devices for virtual reality haptic feedback systems by Dr. Benko, Holtz, Sinclair, and Ofek. Did you always want to touch the fantasy world of virtual reality? Most VR systems these days depend on handheld controllers for input and vibrations for haptic sensations, but vibrational actuators are fundamentally limited in how well they can convey any shape, force, or surface structure to the user. Most force feedback systems in VR suffer from one of these three limitations. 1. They require users to wear an additional gear as in the case of gloves, or 2. They restrict the user's movement to a small working area, or 3. They are handheld and mobile but vibrotactile only. The primary objective that the authors worked on was to provide 3D shape output on the handheld controller form factor. The user should be able to use his virtual fingertip in the VR scene to feel the nuances, resistance, texture, and angle of the object surface. These developments are incredibly important towards overcoming the barriers that we face with virtual reality technology and its applications to the real world. Currently, VR mostly relies on visual and sound feedback, which limits its use for many complex human-computer face interactions, such as manufacturing, surgery, or any type of physical action. To achieve this objective, they presented two designs for haptic controllers called NormalTouch and TextureTouch. They also provided details of how to integrate these systems into the VR scenes and compare them with devices of the current baseline. The first device is called NormalTouch. It physically renders the distance compliance and surface normal of the touch object. In essence, it is a tiltable and height extrudable platform on the actual controller. The core active component of NormalTouch is a steward platform actuated by 3 servo motors. Independent movement of these 3 motors allows adjustment of the height and orientation of the platform. In addition, there is a microprocessor used to communicate with the PC. The principle of operation for NormalTouch is pretty simple. First, it tracks the location of the fingertip on the virtual scene. Then a rake is casted downward from the middle of the finger pad, and if it intersects with the virtual object, then the platform is raised to match the intersection point with the corresponding surface orientation. In addition to rendering the surface height and orientation, NormalTouch uses a built-in force sensing platform to sense the force feedback given by the user, which can then be added to the VR scene. The second device is called TextureTouch, which uses an alternative way to enable shape output underneath the fingertip. The latest version of TextureTouch uses a rack and pinion system to control each individual pin going up with a single servo. This concept is based on servos being stacked in height and depth to fit them into a tight space underneath the fingertip. In contrast to NormalTouch, this design does not support force sensing yet. The principle is similar to NormalTouch, but instead of having one ray, we have 16 rays going down the virtual fingertip, and the surface orientation is not rendered except with the height of each tip. Some of the greatest challenges in haptic rendering arise from the fact that both the device and the platform are moving in space. The feedback is only provided to the finder and not to the hand itself. Since the finger always rests on the platform, the devices don't convey whether or not the finger is on the platform or not. The authors used the technique of penetration compensation to solve some of these limitations. Instead of giving 100% extension on contact touch and penetration, they gave 75% extension to ensure that there was some dynamic range left to adequately render surface variations in height and normal. They then compared non-compensated versions of NormalTouch and TextureTouch with vibrotactile actuation and visual-only systems to test how much they increased the level of fidelity for users in the VR environment. The experiments were conducted with 12 participants, 50% of whom never tried VR. They were given a 15-minute familiarization time to understand 3 different tasks, namely targeting, tracing, and fidelity. The first task involved a person aiming at a specific virtual reality object and pressing a button. The second task involved precisely tracing a specific one-dimensional shape, and the third task needed subjective feedback from the user on how well they were able to perceive the features of the virtual reality object. The main results from these experiments concluded that all of the feedback systems were more accurate than the visual-only feedback. NormalTouch and TextureTouch were significantly more accurate and achieved higher fidelity preference to vibrotactile. These haptic feedback systems have several applications in industry, from video games to 3D modeling. This creation could also greatly enhance the virtual simulations that doctors run through of surgery and other medical practices. Please visit scholar.stanford.edu for more information. As always, thank you for listening to our presentation.